In this video, we're going to talk about optimization. Now, optimization means we're basically finding the local maximum or minimum for a function, because finding an optimal solution means either we're trying to find the maximum of something or we're trying to find the minimum of something. And hopefully this makes more sense with the examples that we do together. Now, this first video will be talking about optimization when we are given the function with which we're trying to find the maximum and minimum. So you'll notice that in your first two steps, I'm leaving the 1 and 2 blank. We're going to come back to this in the next video when we have a little bit more challenging optimization questions. For now, we're going to have questions that they're going to tell us the function in which we want to optimize. For example, if we look at the picture you have on the left, they're showing you taking a sheet of paper and creating it into a box. Well, this situation will probably ask us to find the optimal volume of a box. So we would be given the equation for the volume of a box, and we would have to find its maximum value. So that's what we're going to be talking about today. So the first thing we know that if we're trying to find a maximum or a minimum, we're going to want to differentiate that function. And the derivative is, when the derivative is equal to 0, we know that that's going to be an x value at which we have a maximum or a minimum point. So by setting our derivative equal to 0, we're going to be able to find that x value at which we have either our maximum or minimum. And then, depending on what the question asks, if they're asking you for the value of the function at the maximum or minimum, well, we take that x value that we've got and we can substitute that back into our original function to tell, for example, what is the value of the maximum volume. Let's do some examples to make sense of these steps. A cyclist riding over a hill can be modeled by this function, where the time is between 0 and 70. H is the cyclist's altitude above the mean sea level in meters, and T is the elapsed time in seconds. A, find the derivative of H. So the derivative of H is going to be, so whatever is in front, the number -1 over 24 stays, and then the derivative of T squared is 2T. The derivative of 3t is 3, and the derivative of 12 is 0. So you can simplify this. 2 divided by 24 is going to be -1 over 12t plus 3. Hence, now this is a super important IB command term. Hence always indicates that you must use what came previously, so in this case part A, in order to answer part B. When this key command term hence is used and you do not use part A to answer part B, you're going to be losing out in some of the marks. So if we think about this question, how are we supposed to find the maximum altitude using the derivative? Well, we know that the maximum altitude is going to happen when the derivative is equal to 0. So that means that we need to show that we know that when the derivative is equal to 0, this is going to be the time at which we reach a maximum, and then we'll be able to find what the maximum is. So in our calculators, we can ask the calculator, when is our derivative equal to 0? This is a linear function, so if you use numeric solve, it's going to work, or if you use graphing, any of these will work. So let's go ahead and use graphing, because my calculator is set into a special exam mode, which is fine. So you can use numeric solve if you would like to. I'm going to be using the graphing. So y1 is 1 of my side of the equal sign, so -1 over 12x plus 3. And then I can have the equation y is equal to 0, and I'll be looking for the intersection point. So I don't see the intersection point on my graph, so that means that I'm going to have to restrict the window. I have an indication of what the window should be from 0 to 70, so let me change my window so that I can see 0 and 70. There we go. And then I'm going to find the intersection, first curve, second curve, and yes, and I get that the intersection happens when t is equal to 36. So when our time is equal to 36, that means there will be a maximum. Now, what is the maximum? then we can ask this. So what is the maximum? Then we're going to need to go into our original function and ask what is the value of the altitude when x is equal to 36. And we get that the maximum altitude will be 66. So again, the key important thing for this question is all about this command term. Whenever you see hence, we must use what came before it. Let's go and answer question 2. Example 2, a box of chocolate is to have a ribbon tied around it as shown in the diagram. So we see this little ribbon. The box is in the shape of a cuboid. Cuboid is another word that we use for a rectangular prism. The rectangular prism has a height of 3 centimeters. The length and width of the box are x and y. After going around the box, an extra 10 centimeters for the ribbon. So you can imagine here we have 10 centimeters of ribbon extra. The total length of the ribbon in terms of x is found to be this beautiful equation. Now, this question here, I'd adapted a little bit, and you're going to see in our next video when you're going to have to create these functions. We're going to talk about how we can use the information given to create this function. But for today, the equation is given to us, so let's use the equation given. We're told to first find the derivative of L with respect to x. So first of all, I notice that the way that the function is written, I cannot find the derivative without using the exponent rules to change this. So L can be written as 2x plus 300 times x to the negative 1 plus 22. Now that I've rewritten that middle term, I can in fact find the derivative. So the derivative dl over dx is going to be equal to 2 negative 300 x to the power of negative 2, and the derivative of 22 is simply 0. B, solve when the derivative is equal to 0. So in order to make the derivative equal to 0, I'm going to have to use my calculator, and I'm going to have to use the graphing aspect of the calculator to solve this question. So go ahead and in your calculator, input both functions needed. In our graph, we're going to be seeing there's 2 intersection points. So there's one on each side of the y-axis. So let me change the domain a little bit so we can clearly see that. So there's 2 intersection points. Now, let's think about what x represents. X represents a length. Does it make sense for x to be negative? No. Therefore, we're only going to want to find the point of intersection that has a positive x. So let's go ahead and find that point of intersection. First curve is the blue, second curve is the red, and my cursor is closest to the point that I'm looking for, so I can click on enter. And we get that x is equal to 12.2 if we round to 3 significant figures. Now for part C, another key command term. This one is hence or otherwise. So when you see hence or otherwise means hence you could use what came before in order to help you with this question, or otherwise, or use any other method you want to, right? So very different from example 1. So here we're asked to find the minimum length of the ribbon. Well, the minimum we can find when the derivative is equal to 0. Since I know the derivative since I know that the derivative is equal to 0 when x is equal to 12.2, let's go ahead and use this x value and find what is the length of the ribbon when x is equal to 12.2. And we get that the length of the ribbon is 70.99. So if I round to 3 significant figures, I actually get 71. And I think this is in centimeters, correct?